Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the vast tapestry of the cosmos, where distances stretch beyond human comprehension, scientists have long wondered whether nature provides shortcuts through the fabric of reality itself. These hypothetical passages, known as wormholes, represent one of the most fascinating possibilities emerging from our understanding of Einstein's general relativity. Imagine space-time not as empty void, but as a flexible fabric that can be bent, twisted, and potentially folded. When Albert Einstein and Nathan Rosen first proposed their mathematical solution in 1935, they discovered that the equations of general relativity permitted the existence of bridges connecting distant regions of the universe. These Einstein-Rosen bridges, as they became known, suggested that space and time could form tunnels, linking points separated by millions or even billions of light-years. The concept emerges from the same principles that govern black holes. Just as massive objects curve space-time around them, creating gravitational wells, the extreme curvature required for a wormhole would need exotic matter with negative energy density. This isn't ordinary matter as we know it, but theoretical substances that would repel rather than attract, creating the necessary geometric conditions for a stable passage. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. To understand wormholes, we must first grasp how Einstein's equations describe spacetime as a four-dimensional continuum where massive objects create curvature. Picture a stretched rubber sheet with bowling balls placed on it, creating depressions. Now imagine two such depressions connected by a tunnel beneath the sheet. This analogy, while simplified, captures the essence of how a wormhole might function. As a shortcut through higher dimensional space, the mathematics reveals two distinct types of wormholes. Traversable wormholes would theoretically allow matter and information to pass through safely, while non-traversable ones would collapse before anything could make the journey. The stability of traversable wormholes depends critically on exotic matter with negative energy density, something that remains purely theoretical and may violate fundamental physical principles. Modern physics suggests that quantum effects near the wormhole throat, the narrowest part of the tunnel, would likely destroy any classical wormhole before it could be used. Virtual particle pairs constantly pop into existence and annihilate near the entrance, creating a feedback loop that could cause the passage to collapse in microseconds. Despite these challenges, wormholes occupy a unique position in theoretical physics because they represent solutions to Einstein's field equations that are mathematically valid even if physically implausible. They force us to confront the deepest questions about the nature of spacetime, causality, and the fundamental structure of reality itself. The search for wormholes isn't merely academic speculation. These theoretical constructs help physicists explore the limits of general relativity and probe the mysterious relationship between gravity and quantum mechanics. They serve as laboratories for thought experiments that push our understanding of physics to its breaking point, revealing where our current theories might need revision or replacement. As we stand at the threshold of this cosmic mystery, we must remember that many phenomena once considered impossible have become cornerstones of modern science. Black holes themselves were once mathematical curiosities dismissed by many physicists. Today we photograph their event horizons and detect the gravitational waves they create when they merge. The story of wormholes begins with pure mathematics and human curiosity, but it leads us toward fundamental questions about the nature of existence itself. The mathematical architecture underlying wormholes reveals the elegant complexity of Einstein's general relativity. To comprehend how these theoretical passages might exist, we must explore the intricate geometry of spacetime and the exotic conditions required for their formation. Einstein's field equations describe how matter and energy curve spacetime, with the fundamental relationship expressed as geometry equals mass energy divided by a constant. This deceptively simple statement masks profound implications for how space and time behave near extreme gravitational fields. The Schwarzschild solution, which describes space-time around a spherically symmetric mass, provided the first hints. That reality might contain hidden passages. When Carl Schwarzschild solved Einstein's equations for a point mass in 1916, he unknowingly laid the groundwork for understanding both black holes and wormholes. The complete Schwarzschild geometry includes not just the familiar black hole region, but also a mathematically equivalent white hole region connected through what physicists call the Einstein-Rosen bridge. The geometry of this bridge resembles an hourglass shape in a higher dimensional embedding space. The narrow throat connects two asymptotically flat regions, essentially two separate universes or distant parts of our own universe. However, this classical picture immediately encounters a fundamental problem. The bridge pinches off before anything can traverse it. For a wormhole to remain stable and traversable, it requires what physicists term exotic matter. This hypothetical substance must possess negative energy density, violating the null energy condition that ordinary matter obeys. Imagine matter that creates gravitational repulsion rather than attraction, a concept that challenges our everyday intuition about how mass and energy behave. The amount of exotic matter needed is staggering. Calculations suggest that keeping a 1-meter-wide wormhole open would require negative mass energy, equivalent to the mass of Jupiter. This exotic matter must be distributed precisely along the wormhole's throat, creating an outward pressure that counteracts the natural tendency of the passage to collapse under its own gravitational field. Quantum field theory offers tantalizing hints that exotic matter might exist in nature. The Casimir effect demonstrates that quantum vacuum fluctuations can produce negative energy densities between parallel conducting plates. Two metal plates placed extremely close together experience an attractive force because quantum fluctuations between them have lower energy than those in the surrounding vacuum. However, scaling these quantum effects to macroscopic wormholes presents enormous challenges. The Casimir effect produces negative energy densities on microscopic scales, but whether nature permits the large-scale exotic matter distributions required for traversable wormholes remains an open question. Theoretical physicists have proposed various solutions to the exotic matter problem. Some models suggest that advanced civilizations might manipulate space-time using negative energy created by moving mirrors or rotating cylinders at near-light speeds. Others explore whether certain quantum field configurations could naturally produce the required exotic matter distributions. The wormhole metric, the mathematical description of space-time geometry around these passages, reveals additional complexities. The proper time experienced by travelers through the wormhole depends critically on the specific shape of the throat and the distribution of exotic matter. Slight variations in these parameters could result in extreme tidal forces that would destroy any material object attempting passage. Morris-Thorne wormholes, named after physicists Michael Morris and Kip Thorne, represent the most studied class of traversable wormholes. Their 1988 paper established the mathematical framework for analyzing these structures and identified the fundamental requirements for safe passage: minimal tidal forces, reasonable travel times, and structural stability, the C. Geometry must satisfy specific boundary conditions to ensure that travelers entering one mouth emerge from the other, rather than being crushed or trapped within the throat. This requires careful engineering of the exotic matter distribution and precise control over the wormhole's shape. Understanding wormhole architecture pushes the boundaries of our mathematical tools and physical intuition, preparing us to explore their potential role in the broader cosmos. The search for wormholes represents one of astronomy's most challenging endeavors, requiring scientists to identify subtle signatures that might distinguish these exotic objects from more conventional cosmic phenomena. Unlike black holes, which announce their presence through powerful radiation from their accretion disks, wormholes would likely remain hidden unless we know exactly what to look for. Gravitational lensing offers the most promising avenue for detecting wormholes. When light passes near massive objects, space-time curvature bends the light rays, creating magnified or distorted images of background sources. Einstein's general relativity predicts that wormholes would produce distinctive lensing signatures that differ subtly but measurably from those created by black holes or other compact objects. The key difference lies in the light rays that pass through the wormhole throat. While a black hole creates a shadow, a dark region where no light can escape, a traversable wormhole would allow some light rays to pass through the throat and emerge from the other mouth. This creates a complex lensing pattern with additional bright spots and rings that don't appear in black hole lensing. Astronomers using the Event Horizon Telescope, the same international collaboration that captured the first images of black holes, are developing techniques to distinguish between black hole and wormhole shadows. The wormhole shadow would contain a bright spot at its center, created by light traveling through the throat from the region behind the far mouth. Gravitational wave astronomy offers another detection method. When two wormholes merge, or when objects fall through a wormhole, they would produce gravitational wave signatures distinct from known sources, like merging black holes or neutron stars. The Laser Interferometer, Gravitational Wave Observatory, or LIGO, and its international partners continuously monitor space-time for these ripples. The gravitational wave signature of a wormhole merger would differ from a black hole merger in subtle but detectable ways. The final stages of the waveform, called the ring-down phase, would show different frequency patterns because wormholes lack the event horizon that characterizes black holes. Advanced data analysis techniques are being developed to identify these distinctive signatures in future observations. Microlensing surveys present another opportunity for wormhole detection. These projects monitor millions of stars simultaneously, looking for temporary brightness increases caused by intervening massive objects. A wormhole passing between Earth and a distant star would create a characteristic light curve, a pattern of brightness variation over time that differs from conventional microlensing events. The optical gravitational lensing experiment, known as OGLE, and similar surveys have catalogued thousands of microlensing events over the past 2 decades. Researchers are now reanalyzing this data, using sophisticated algorithms designed to identify potential wormhole signatures that might have been overlooked in previous searches. Radio astronomy provides additional search strategies. If wormholes exist naturally in our galaxy, they might occasionally capture and channel radio signals from distant sources. A radio telescope observing a wormhole throat might detect signals originating from the far mouth, potentially located thousands of light-years away. The Very Large Array in New Mexico and the Atacama Large Millimeter Array in Chile regularly survey the sky for transient radio sources. Advanced signal processing techniques could potentially identify radio bursts with the distinctive spectral characteristics expected from signals traveling through wormhole throats. Theoretical models suggest that primordial wormholes, formed in the early universe during periods of rapid expansion, might still exist today. These ancient structures would be incredibly small, with throats measured in subatomic dimensions, but they could potentially be detected through their gravitational effects on nearby matter. The search extends beyond our own galaxy. Astronomers are examining distant quasars and active galactic nuclei for signs of wormhole activity. If supermassive wormholes exist at galactic centers instead of black holes, they would produce subtly different patterns of matter accretion and energy emission. Current observational capabilities limit our ability to definitively identify wormholes, but advancing technology continues to expand our detection possibilities. Future space-based telescopes and gravitational wave detectors will provide unprecedented sensitivity to the exotic signatures these cosmic tunnels might produce. The hunt for wormholes pushes observational astronomy to its limits, demanding new techniques and innovative analysis methods. Traversing a wormhole would subject travelers to some of the most extreme physical conditions imaginable, challenging every aspect of our understanding of space, time, and matter. The journey through these hypothetical cosmic tunnels reveals fundamental physics operating at the very limits of what nature might permit. The approach to a wormhole mouth would initially resemble falling toward any massive object. Gravitational acceleration would increase steadily, but the exotic matter required for wormhole stability creates unprecedented conditions. Unlike ordinary matter that attracts, the negative energy density of exotic matter produces gravitational repulsion near the throat. This creates a complex gravitational environment where tidal forces, the differential gravitational pull on different parts of an object, could either stretch travelers beyond their breaking point or compress them catastrophically. The specific geometry of the wormhole throat determines whether passage is survivable or instantly lethal. Morris-Thorne wormholes, designed for safe traversal, require the exotic matter to be distributed precisely to minimize tidal forces. Calculations show that a human could survive passage through a wormhole with a throat radius of approximately 1 kilometer, provided the exotic matter creates the correct gravitational gradients. Smaller wormholes would generate tidal forces exceeding the tensile strength of human tissue. The passage through the throat itself defies conventional understanding of space and time. Distance measurements become ambiguous in the highly curved space-time near the wormhole center. A traveler might experience crossing a region only meters wide that connects points separated by millions of light-years in normal space. Time dilation effects would depend critically on the wormhole's specific geometry and the distribution of exotic matter. Unlike the predictable time dilation near black holes, wormhole time effects could vary dramatically based on construction details. Some theoretical models suggest that clocks would run faster inside the throat due to the negative energy density, while others predict more complex temporal distortions. The visual experience of wormhole travel would be extraordinary and disorienting. Light rays following curved paths through the exotic space-time would create a tunnel-like view ahead, with the destination slowly expanding from a point to fill the entire forward view. Behind the traveler, the departure point would contract to a bright spot, eventually disappearing entirely. Electromagnetic effects inside the wormhole could prove problematic for both travelers and their equipment. The exotic matter required for stability might interact with electromagnetic fields in unexpected ways, potentially disrupting electronic systems or creating dangerous radiation exposure. The quantum vacuum state inside the throat differs fundamentally from that in normal spacetime. Quantum effects become crucial near the wormhole throat, where spacetime curvature reaches extreme values. Virtual particle pairs created by vacuum fluctuations could accumulate near the throat, potentially creating a quantum avalanche that destroys the wormhole before passage is complete. This represents one of the most serious theoretical obstacles to traversable wormholes. The semi-classical approximation, treating gravity classically while considering quantum effects of matter fields, suggests that quantum back reaction would likely destabilize any macroscopic wormhole. As soon as the first particles attempt passage, their quantum interactions with the exotic matter could trigger catastrophic collapse. Temperature effects inside the wormhole remain poorly understood. Some calculations suggest the exotic matter might create regions of negative temperature, not merely cold, but possessing less thermal energy than absolute zero. Such conditions would fundamentally alter the behavior of any ordinary matter attempting passage. The acceleration profile during transit determines both the subjective experience and physical stresses on travelers. Optimal wormhole geometries would provide smooth acceleration and deceleration, minimizing discomfort and physiological effects. However, maintaining such precise conditions while preserving stability presents enormous engineering challenges. Communication through the wormhole would face unique obstacles. Radio signals traveling through the throat would experience frequency shifts and temporal delays that differ from those in normal spacetime. The exotic matter might act as a filter, allowing some wavelengths to pass while absorbing others completely. Exit from the far mouth would mirror the entry process in reverse, but with the added complexity of emerging into potentially different physical conditions. If the wormhole connects distant regions of the universe, travelers might encounter different background radiation levels, magnetic field strengths, or even slightly different physical constants. The round-trip journey would test the fundamental limits of physics, requiring unprecedented understanding of exotic matter behavior and quantum gravity effects. The existence of traversable wormholes would revolutionize our understanding of the universe and humanity's place within it, fundamentally altering concepts of distance, time, and the very nature of reality. These cosmic passages represent far more than mere shortcuts through space. They embody gateways to unprecedented possibilities and profound philosophical questions. For space exploration, wormholes would transform humanity from a single-planet species confined to one small corner of the galaxy into potential citizens of the entire cosmos. Journeys that would require thousands of generations using conventional propulsion could be completed in hours or days through wormhole passages. The nearest stars, currently separated from us by decades of travel time even at relativistic speeds, might become as accessible as neighboring continents. The implications extend beyond simple transportation. Wormhole networks could enable instantaneous communication across galactic distances, creating a cosmic internet that connects civilizations separated by millions of light-years. Information, knowledge, and culture could flow freely through these passages, fostering unprecedented collaboration and understanding among intelligent species throughout the universe. However, wormholes also present the possibility of causality violations that challenge our understanding of cause and effect. If wormholes can connect regions of space-time with different temporal coordinates, they might permit closed time-like curves, paths through space-time that loop back to their own past. This raises the specter of grandfather paradoxes and other temporal anomalies that seem to violate fundamental logical principles. Theoretical physicists have proposed various solutions to these causality problems. The Novikov self-consistency principle suggests that the laws of physics would somehow prevent paradox-creating actions, ensuring that timeline alterations are either impossible or self-correcting. Alternatively, many worlds' interpretations of quantum mechanics propose that timeline changes create parallel universes rather than paradoxes. The study of wormholes drives advances in quantum gravity, the elusive theory that must eventually unite Einstein's general relativity with quantum mechanics. String theory, loop quantum gravity, and other approaches to quantum gravity all make specific predictions about wormhole behavior and stability. Discovering actual wormholes would provide crucial tests of these fundamental theories. Holographic duality, emerging from string theory research, suggests that wormholes might be dual to quantum entanglement, that Einstein-Rosen bridges and quantum mechanical correlations represent different descriptions of the same underlying physical reality. This ER equals EPR conjecture, named after Einstein-Rosen bridges and Einstein-Podolsky-Rosen entanglement, could revolutionize our understanding of both space-time and quantum mechanics. The search for wormhole signatures pushes astronomical instrumentation to unprecedented levels of precision and sensitivity. Future gravitational wave detectors, like the Laser Interferometer Space Antenna, or LISA, will monitor space-time fluctuations with exquisite accuracy, potentially detecting the subtle signatures of wormhole activity across cosmic distances. Next-generation telescopes, including the extremely large telescope and space-based successors to the James Webb Space Telescope, will scrutinize black hole candidates with unprecedented resolution. These observations might reveal the telltale differences between black hole shadows and wormhole lensing patterns, finally answering whether these exotic passages exist in nature. The practical engineering of traversable wormholes, should they prove physically possible, would require mastery of exotic matter production and manipulation. This technology would represent one of the greatest achievements in the history of science, comparable to the development of nuclear energy or semiconductor electronics in its transformative potential. Such capabilities would also raise profound ethical questions about access, safety, and the responsibility that comes with manipulating the fundamental structure of space-time. The power to create shortcuts through the universe carries risks commensurate with its benefits, potentially affecting not just human civilization, but the stability of space-time itself. Current research continues to refine our understanding of what wormholes might require and how they might behave. Advanced computer simulations model the complex interactions between exotic matter, quantum fields, and curved space-time, providing increasingly detailed pictures of these hypothetical structures. The quest to understand wormholes ultimately reflects humanity's deepest curiosity about the nature of existence. Whether these cosmic tunnels exist naturally, can be artificially created, or remain forever beyond physical possibility, their study illuminates the fundamental principles governing our universe. In pursuing the mystery of wormholes, we push the boundaries of human knowledge and technological capability, preparing for a future where the impossible might become inevitable. The journey toward understanding these cosmic gateways continues to reveal new depths in the elegant mathematical structure that underlies all of reality, reminding us that the universe still holds secrets waiting to be discovered.